Hi, I'm Tate from Cornell University, and I'm here to present Sequential Semantics of Producer Effect Systems. Now, this title has a number of terms in it that have some confusion about them, partly because some of them I just made up myself. So I'm just going to begin by explaining what I mean by this title, starting with the word effect. So if we consider computation, sure, it has inputs and outputs, and we use types to classify what those inputs and outputs look like. But this talk isn't about types. This talk is about effects. So how do effects fit into this picture? Well, an effect, rather than being a classification of the interface of a computation, an effect is a classification of the internals of a computation. So for example, we might say that inside this computation, we don't always use all our inputs. Or inside this computation, we sometimes will leak information and violate some security policy. Or inside this computation, we might throw an exception and not even actually produce the outputs we say we output. And so effects can take a variety of forms, and languages actually will have many effects in them. And so because of that, I don't want to focus just on a effect. I want to focus on community effects, all of which are interacting with each other. And so I care about effect systems. And to show what an effect system might look like, let me present one that's sort of meant to classify the locking behavior of various programs. And the reason why we want one of these is that suppose we have two acquire operations in a row. That is, two computations grabbing some global lock. The first computation is going to grab the lock, and then the second computation is going to try to grab the lock. And, and the second computation is going to fail, right? Because the locks are going to be already acquired, and this can lead to a deadlock. So we'd like to prevent these kinds of computations so we can prevent these deadlocks. And unfortunately, types aren't going to work for us here. The issue is that neither of these computations have any inputs and outputs, so no matter what type we give them, we're not going to be able to solve this problem. So rather than using types, we're going to use effects. And what we do is say both of these operations have the locking effect. And in general, if we have any two locking computations guaranteed to acquire the lock, we're going to run into the same situation. So we'll say that two locking computations can't be sequenced together. And so by using effects in order to the validity of a program, we can we can use effects to affect the validity of a program in order to prevent deadlocks. And we'd like to prevent more than just deadlocks when we're doing synchronization. We'd also like to prevent race conditions. So what we're going to do is say, let's look at this operation get. This thing will access shared memory, and so we want to make sure it's run only inside a critical region. So what we're going to do is say it has the critical effect, meaning that this should be run only inside critical regions. So in particular, if we have an acquire before and a release after, this looks great. And we're going to code that in our effect system by saying that whenever we have a locking computation followed by a critical computation followed by unlocking computation, this is fine, and the overall effect is what we call an entrant computation. That is something that temporarily enters a critical region. And so with this picture, we get the beginnings of an effect system. So let's formalize this effect system a little bit more. We've already seen that there's 4 effects regarding locking behavior, but it turns out there's one more effect that we'd like to have, namely the loftless effect, which we'll use to classify all those computations which may not necessarily be pure, but whose effect at least has nothing to do with the locking behavior of the program, and so we're not going to worry about it. And these 5 elements form the basis of an effect system. But an effect system is more than just its elements. An effect system is also how these elements interact with each other. So we'd like to say what happens when one effect is followed by another effect, which we use as Blackboard semicolon to denote. And you can use the reasoning I showed you on the previous slide in order to say that here's a complete table of how all these effects interact. And sometimes we'll say that 2 effects shouldn't be sequenceable in order to prevent deadlocks. And so we get beginnings of a formal effect system. But we're not done yet. Particularly, we have to worry about how this effect system handles pure computations. So let's consider this divide by 2 operation. How can we classify this operation? Well, first, we can call it a lockless computation. After all, it has nothing to do with locking behavior, and that's what lockless is for. Turns out we can also call it a critical computation. Sure, we're restricting its usage, but that restriction is at least safe to do. And for same reasons, we can call it an entrant computation. And in general, this reasoning says that any lockless computation can be treated as either critical or entrant. And so we got those 3 effects covered. But what about the locking effect? Remember that locking effect is used to ensure that we're inside a critical region. And so we need locking computations to actually acquire a lock, which this computation does not do. So we can't give this pure code the locking computation or locking effect. And similarly, we can't give it the unlocking effect. And so we divided our effects into these two groups. The top group basically describes may properties, things that might happen. And so in particular, pure code can be assigned to it. Whereas the bottom group can be are must properties. And so since this pure code doesn't do anything, it doesn't satisfy these must properties. And thus, we're going to code this into our formalization with this blackboard epsilon notation, saying that the lockless entrant and critical effects can be assigned to pure code. Furthermore, our observation that lockless code can always be treated as either critical or entrant code tells us that the lockless effect is a sub-effect of both the critical and entrant effects. And with this picture, we finally have a complete formalization of our locking effect system. And what's interesting about this effect system is that even though it's small and intuitive, its semantics actually cannot be formalized by any of the pre-existing semantic frameworks out there. In particular, if we were to try to use a monad, we could formalize just the lockless effect. If we were to try to use an index monad, we could add one more effect. If we were to try to use layered monads in action, we can add yet one more effect, but there's still this big hole here. And what I proved is that any framework using monads only is always going to have this big hole because monads cannot be used to formalize must properties. In particular, the unit operation guarantees that they can only formalize may properties. Fortunately, there are some other frameworks out there, such as parameterized monads, which can handle locking and unlocking effects, which are must properties. But as a consequence, it can't handle the lockless effect anymore. And so if we want to handle the entire effect system, what we need to use is what I call a productoid. It's named so because it's a monoid-like formalization of producer effect system. And there I go, making up terms again. So let me explain what I mean by a producer effect. So if we consider an effectful computation, this effect is a producer effect if semantically we can represent it as some pure formalization with the same input but a modified output. And this modified output describes how that effect alters what that computation can produce. So for example, if we have the partial effect, describe it with this maybe output, indicating that maybe it'll output something, but maybe it won't output anything. And it turns out that all our locking effects I just showed you can also all be described as producer effects. The lockless effects we're going to describe abstractly so that we can have a nice extensible semantics. Whereas the locking effect, we'll say, is something that needs a lock in order to execute, and then after running for a while, it eventually will give us the capability to access shared memory when it's done. And these L and C are abstract types that we use to denote the lock and the capability. And we reuse them in all the other effects in order to, in a similar way. And thus we get here a producer effect system. And now that we finally have a producer effect system, I can get on to the meat of this talk, which is the sequential semantics of these producer effect systems. And this is what I call a productoid. And a productoid is made of a number of parts. And rather than showing you all those parts at once, I'm going to show them to you bit by bit as they're needed in order to formalize the semantics of computations. So to begin, what happens when we have a critical code followed by pure code? How can we denote this semantically as some pure formalization? Well, the critical code is a producer effect. So we know that semantically represent this as something with this modified output here. And now we want to output or sequence that computation with this divide by 2. But we run into a problem here, which is that divide by 2 expects a normal integer, and now we're outputting a modified integer. And this is sort of the critical problem for handling effects. So how can we get around this? Well, our one formal assumption about effects is that if we have an effectful computation followed by a pure computation, then the pure computation shouldn't change the overall effect. That's the whole point of being pure. And so this should overall have the critical effect. And knowing that, since critical effect is a producer effect itself, that tells us that we should be able to represent this as something that has this modified number as its output. And this leaves us this little hole here that we want to fill. So it's exactly what a productoid does. It says that whenever you have an effect, there needs to be a map operation which shows how to fill in this hole. In particular, it shows how to propagate effects through pure computations. Now, this is sort of the simplest picture of the whole system. Let's consider something a little more advanced to really get a sense of how these effect systems work. In particular, let's consider sequencing two different effectful computations together. Well, both of these are producer effects. So we can represent them semantically with this modified output. And this leads us to the same problem where the second's output no longer matches with the first input, but we can reuse that concept of mapping in order to lift the second computation and propagate that first effect through the second computation. But this time we're mapping something that already had an effectful output. And so we get something as a result that has this doubly effectful output. That is, it's modified both by the original effect and by the second effect. And if we keep doing this, things will blow up, especially if we start considering things like for loops and recursion. So we need to figure out a way to simplify this picture. The thing we're going to take advantage of is that the fact we don't need to compose arbitrary effectful computations together. We only need to compose effectful computations together for which the effect system says should be composed into some overall effect. And this overall effect is, again, a producer effect. So that tells us that we should be able to represent this semantically as something with this singly effectful output. And this, once again, leaves us with a hole to fill. And so what a productoid does is says that whenever the effect system says there's a valid sequencing of effects, there needs to be a join operation which shows how to simplify a doubly effectful value into a singly effective value of the right type. Now, this is beginning to look a lot like monads, which we're all used to. But note that a monad requires all of these three effects to be the same effect. And in fact, all of the existing formalizations impose some sort of unnecessary restriction on this picture here, which is what limits their capability to represent effect systems. And so because of that, they have this productoid. And so to recap, a productoid has a map operation for every effect showing how to propagate it through pure code. And it has a join operation for every sequencing permitted by the effect system showing how to simplify doubly effective values into singly effective values, which when combined with the map operation gives you a way to sequence computations together. What I haven't shown you is that there's also a chorus operation for every sub-effecting inner system showing how to convert sub-effectal values to super-effectal values. And there's a unit operation for every effect that can be assigned to pure code showing how to turn pure values into effectful values. But note that we only need the unit operation when the effect system says this effect should be applied to pure code. We don't always need it, which is where we differ from monads, which is what allows us to handle these sort of must properties and such. And in general, looking at this picture, all these operations are only required when the effect system actually needs them. And because of that, what I was able to prove is that the sequential semantics of any producer effect system is guaranteed to form a productor. And so since all those existing frameworks implicitly assume that they were using these producer effects, they are automatically guaranteed to be instances of this framework. And the reason why they make that assumption is that producer effects are actually extremely common in programming languages for a good reason. In particular, what I proved is that if you have any effectful language with some notion of thunking computations into pure values, then it's going to be comprised of only producer effects. In particular, what this means is that if your language has a notion of either computations or functions as pure values, then you're going to form a productor. And so that fundamental concept links to this semantic framework here. Now, what's particularly interesting to consider is that we have all those other existing frameworks, which are various specializations of productors as a result of this. And they actually all are built from various properties of the effect system. So particularly, if you build a productor from a single effect, then you're going to get Moggi's monads. And if you build a productor from a joint semi-lattice effects, you're going to get Waller and Thiemann's index monads. And if you use a partial joint semi-lattice effects, then you're going to get Felinsky's layered monads in action. And if you're going to use an effect system for state transitions, then you get Atke's parameterized monads. And furthermore, what it proves is that these are all if and only ifs. That is, these are the only kinds of effect systems that those can describe. And what this is important for is that our locking effect system does not quite fall into any of these categories. And so as a result, it can't be described by any of the existing frameworks. And this is a shame because productors can be quite useful in verifying various properties. So by building a productor for this effect system on the right semantic domain, namely one where we have these abstract operations for, say, acquire and release, which exchange the lock with the capability, and for get and set, and consequently have the locking and unlocking effects, and for get and set, which access and write the shared memory, provide this capability as present, and so have to be given the critical effect. In this semantic domain, we're guaranteed that all computations only access shared memory and inside critical regions, and no computations will ever deadlock. And so by having a productor for our effect system that compiles to the semantic domain, we automatically get those guarantees without any additional effort. Furthermore, when we build this productor, we actually learn a useful lesson about these lockless effects that sort of trended over. Particularly, we find out that the lockless effect needs what's called linear strength. That is a way to pull a resource inside this lockless effect. And this actually isn't a problem for things like heaps or non-determinism, randomness, state, so on. And so this result tells us that all those effects can be added to our language without any problem. But there is actually a problem for exceptions. Exceptions don't have this property, and that tells you that exceptions can't be included inside the lockless effect. So if you did that, we'd catch this bug right here, and then we get around that problem. And if you wanted to have exceptions, then this tells you that you need to make a more rich effect system in order to track both exceptions and locking simultaneously, which made for a fun assignment for my class last semester. So using a productor, we're able to get these nice, strong guarantees for this very simple effect system and get some insights on how we can work with this language and extend it. But there's one thing in all of this that I sort of look past over, which is we have this productoid, and it has all these operations. And all these operations are going to be combined together in order to sequence computations. And we want them to interact nicely. And particularly, we want sequencing computations to be, say, associative, or we want inlining of functions to preserve semantics and stuff like that. And so we need some equational constraints on these operations. Now, the map operation turns out it needs to be a form of functor. And all these join, chorus, and unit operations need natural transformations for those functors. But that's sort of the boring part. The more interesting part is considering how these join, chorus, and unit operations interact with each other. And basically, this is our analog to the monad laws. And it turns out that there's actually a better way to view this picture if we generalize a tiny bit. In particular, what we should observe is that all these operations take a value of varying degree of effect and simplify it down to a singly effectful value. And so if instead we formalize our effect systems through saying that suppose we had some list of effects are sequenced together, then this is the overall effect. This formalization I call an effector. It's slightly more general than I showed you before. Then for every such sequencing permitted by this effector, a productor will provide a join operation turning a multiply effectful value into a singly effectful value. And then these old join, chorus, and unit operations are all just special cases of this one operation, namely the binary case, the unary case, and the nullary case. And so we don't need them anymore. And we can just use these join operations. And now we have this picture, we can actually describe all our equational properties for our system with just one equation rather than a whole bunch of equations. In particular, suppose we have a many effectful value. So many effects that we're going to try to tackle this problem of simplifying this piece by piece. So we're going to simplify, say, the first group of effects, the last group of effects, just various lists of effects together in order to get a new list of effects that's a little bit smaller. And then we're going to simplify all those little effects, join them together into one effect at last to get our singly effectful result. And so through this process, we get sort of an indirect way of combining effects together. And what's interesting, important about the design of effectors and productors is that they guarantee that in this situation, there will also always be a direct way to combine these effects together, just in one step. And so now that we have this indirect path and this direct path, our one equational requirement is that whenever this is possible, then these two paths need to be equal to each other. And the monad laws and such are all just special cases of this equality. And so with this, we get a nice simplified picture of what's going on with effects, and a sort of higher framework is how we might manipulate with them. And so, concluded at this point, what I've done here is give a formalization for the sequential aspects of effects, using effectors to formalize the static properties of effects and productors to formalize the semantic properties of effects. And I also showed exactly when these kinds of formalizations can be applied. In particular, these productors are guaranteed to be applied to any producer effect system. And these producer effect systems are common in our system because we have this basic assumption that computations and functions are values. And so lastly, the thing I want to talk about is, in this research, I came up with a number of interesting new topics to look into. One of which is the idea of consumer effects. That is, rather than classifying what I produce, let's classify how my computation consumes its inputs. And it turns out that I already solved part of this problem. If you want to formalize the semantics of consumer effect systems, you use what I call a consumptor just by dualizing all the stuff I just showed you for productors, and you get a solution. And it's guaranteed to be just as general and stuff like that. But what's more interesting is that there seem to be some interesting things that arise when you consider the interaction of consumer effects and producer effects. In particular, laziness and strictness seem to arise just by toggling how one producer effect interacts with one consumer effect. And just by flipping that switch, you get lazy or strict. And searching that might give us some more insights into how our languages work. But that's all in progress, and there's a lot more work I want to do in this area, but I've already taken enough of time, so at this point I'd like to thank you guys for your attention and open up to any questions you may have.